Hello students, in the present video session we will learn about pipelining as a means for executing machine instructions concurrently, various hazards that cause performance degradation in pipeline processes and means for mitigating their effect, hardware and software implementations of pipelining, influence of pipelining on instruction set design as well as superscalar processes. So first we'll consider overview. Pipelining is widely used in modern processes. So we can adopt the concept of pipelining in the case of modern processes. Pipelining also improves the performance in terms of throughput. So we can improve the performance of the system by considering pipeline concept in terms of throughput. Pipeline organization requires sophisticated compilation techniques. So the basic building blocks of a computer are introduced in the previous sessions. So here we'll discuss in detail the concept of pipelining, which can be used in modern computers in order to achieve high performance. So in the case of pipelining, we can consider how it can lead the improvement of performance. So also we can examine machine instruction features that facilitate pipeline execution and which will show that the choice of instructions as well as instruction sequencing can have a significant effect on the performance. So basically we have to consider the performance as a factor, and by adapting the pipeline concept, so it specifies how we can improve the performance. Pipeline organization requires sophisticated compilation techniques as well as optimizing compilers have been developed for this purpose. Among other things, such compilers rearrange the sequence of operations. So here in the case of pipelining, we can rearrange the sequence of operations so that we can get the maximum benefits of pipeline execution. So now we'll consider basic concepts. The speed of execution of programs is influenced by many factors. So we know that the speed of execution of the program, it will be depending upon some set of factors. So we need to improve the speed of operation or speed of execution of a program. The one way to improve the performance is to use the faster circuit technology. So we need to adopt faster circuit technology in order to build the processor and the main memory. So while constructing the processor as well as main memory, so we have to use faster circuit technology. So one more possibility in order to improve the performance is the possibility to arrange the hardware so that more than one operation can be performed at the same time. So that means we are overlapping the operations. So we are parallelly or sequentially we are operating or we are executing the operations. So that means we have to arrange or we have to construct the hardware so that we have to execute one or two or more programs parallelly. So if you are adopting these two techniques, so we can improve the performance. The number of operations performed per second is increased even though the elapsed time needed to perform any one operation is not changed. So we are not changing the elapsed time to perform that operation or that respective operation. Irrespective of that, what we are doing is, so we are improving or we are considering the number of operations that can be performed per second can be improved. So pipelining is a particularly effective way of organizing concurrent activity in the computer system. So in order to improve the performance of the computer, so we can adopt pipelining concept so that we can improve the activities with respect to a computer system. The basic idea, which is very simple, it is frequently encountered in a manufacturing plants where pipelining is commonly known as an assembly line operation. Readers are undoubtedly familiar with the assembly line used in car manufacturing. The first station in an assembly line may prepare the chassis of a car. The next station adds the body, and the next one install the engine, and so on. So while one group of workers is installing the engine on the car, other group is fitting a car body on the chassis of another car, and so on. So that means in short we can say that we are overlapping the operations. So now we'll consider how the idea of pipelining can be used in a computer. The processor executes a program by fetching the executing instruction one after the other. So that means in the previous sessions we considered the processor can execute only one instruction in the given instant, and the processor can execute the instruction sequentially one after the other. So if you suppose if you are considering suppose if you are having some set of instructions like F1, E1, F2, E2, F3, E3, and so on. So here I'll consider Fi and Ei refers to the fetch and execute steps for one instruction, that is II. Execution of a program consists of sequence of fetch and execution steps. So we know that each time we have to the processor need to fetch an instruction. After fetching the instruction, the next phase will be decode phase, and after decoding the instructions can be executed. So here we are overlapping some sort of instruction execution phase as well as fetch phase so that we can improve the performance of the system. So making the execution of programs faster. Use faster circuit technology to build the processor and the main memory. Arrange the hardware so that more than one operations can be performed at the same time. In the later way, the number of operations performed per second is increased even though the elapsed time needed to perform any one operation is not changed. Traditional pipeline concept. So we'll consider one laundry example. Anne, Brian, Kate, and Dave each have one load of clothes to wash, dry, and fold. So we know that in the present example, we consider the washer will take around 30 minutes to wash all the clothes, as well as the dryer takes around 40 minutes to dry, and the folder takes around 20 minutes to fold the clothes. So here we have to perform the operation in sequentially. So after washing all the clothes, after around 30 minutes, so the dryer can start its operation. Once again, the dryer will takes around 40 minutes to perform the task, and the folder will take around 20 minutes to perform the task. So in the traditional pipelining, so we need to have, in order to complete all the operations, we need to consider 30 plus 40 plus 20 minutes. So here the sequential laundry, which takes around 6 hours for 4 loads. So if you are performing the operations sequentially one after the other, the laundry will take around 6 hours for 4 loads to complete wash, dry, as well as folding task. If they learn pipelining, so we can consider how long would laundry take to complete all the operations. So the traditional pipeline concept. So here we can observe that the task order is considered. So we can consider we can overlap the process here. We are overlapping the process here, and if you are overlapping the process, the pipeline laundry takes around 3.5 hours for 4 loads. Pipelining does not help latency of single task. It helps throughput of entire workload. Pipeline rate limited by slowest pipeline stage. Multiple tasks operating simultaneously using different resources. Potential speed up, that is nothing but the number of pipeline stages. Unbalanced length of pipe stages reduces the speed up. Time to fill pipeline and time to drain, it reduces the speed up. And stall for dependencies. So here, in the case of pipelining concept, if you are not adapting overlapping of the operations, it takes longer time to complete the entire task. So instead of that, if you are considering the pipeline concept, so we can reduce the amount of time required to complete the given task. So now we can consider the use of idea of pipelining in a computer system. So as I mentioned before, we have to overlap the operation of fetch phase as well as execution phase. Now consider a computer system which has two separate hardware units. One for fetching the instruction and another for executing the instruction. So we considered one hardware organization, so which has two separate hardware units. One is in order to fetch the instruction and another unit which will execute the instruction. The instruction fetched by the fetch unit is deposited in an intermediate storage buffer. So after fetching the instruction, those fetched instructions will be stored within the internal storage buffer B1. So this is the internal storage buffer B1. This buffer need to enable the execution unit to execute the instruction while the fetch unit is fetching the next instruction. So what is the condition here is, from the buffer interstage buffer unit, the instruction will be moved into the execution phase. Parallelly, the instruction fetch phase, it will fetch the next instruction. The results of execution are deposited in the destination location specified by the instruction. For the purposes of this pipelining concept, so we can assume that both the source as well as destination of the data operated on by the instructions are inside the label block as execution unit. So within the execution unit itself, we can store the final result, and as per the application requirement, the result can be fetched from result can be copied from the execution unit. So the computer is controlled by a clock whose period is such that the fetch and execute steps of any instruction can each be completed in one cycle. So we are assuming that within one clock cycle, so we have to complete the execution phase as well as fetch phase. The operation of the computer is considered in this example, that is pipeline execution. So in the first cycle, we can assume that during this first cycle, the fetch unit fetches the first instruction. This one. and stores it in the buffer register B1. It will store it in the buffer register B1. So during first clock cycle, the instruction unit, it will fetch the first instruction, that is I1, and it will store that I1, that is the instruction 1, in the buffer register B1. So similarly, during second clock cycle, so we can observe that the instruction fetch unit, it will fetch the second instruction. The instruction fetch unit, it will fetch the next instruction, that is I2. So meanwhile, so from the inter-stage buffer register B1, so the instruction will be copied into the execution unit and it will start its execution. So that means during fetch phase of I2, so we can execute the first instruction. So similarly, we can observe that during clock cycle 3, the instruction fetch unit, it will fetch the next instruction, that is I3, and so during the same clock cycle, that is clock cycle 3, during clock cycle 3, we can observe that we can fetch the next clock instruction, that is F3, and execution of E2 will takes place. So that means by the end of this second clock cycle, the execution of I1 is completed. So I can observe that during end of this clock cycle, execution of E1 is completed. During end of clock cycle 3, execution of E2 will be completed. During E4, the execution of I3 will be completed, and so on. Each time while executing or after fetching the instruction will be copied into B1. So that means the interstage buffer register, in order to fetch the next instruction by the instruction fetch unit. So the fetch and execute unit can be overlapped so that we can improve the stage-wise performance, and we can perform the both instruction execution as well as instruction fetch phase parallelly. So during fetch phase, read the instruction from the memory can take place. So after that, the instruction need to be decoded. So finally, during the next phase, so we have to execute the instruction. Finally, we have to copy the result in the respective destination location. So here we can observe that in diagram A, we can consider that the sequential execution of instruction is given. So that means I have to, the processor will fetch F1, it will execute E1. The next, after execution of first instruction, the processor will fetch F2, it will execute E2. So after completion of the second instruction I2, it will fetch F3, execute E3. So this is nothing but sequential execution. So here we can consider the instruction pipelining. So where we can overlap execution as well as fetch phase between the instructions. So during clock cycle 1, I can say that the instruction 1 is fetched. During clock cycle 2, instruction 1 can be executed, and similarly parallelly the second instruction can be fetched, and so on. So that is nothing but pipeline execution of the instructions. So use of idea of pipelining in a computer. So that means we are overlapping or we are considering fetch, decode, execution and write phase together. So F is nothing but fetch phase of instruction 1, D1 is nothing but decode phase of instruction 1, E1 is nothing but execution of instruction 1, W1 is nothing but write phase of instruction 1, and similarly for I2 we consider F2, D2, E2 and W2 and so on. So the diagram shows instruction execution divided into 4 steps like instruction fetch phase, instruction decode phase, instruction execution phase and instruction write phase. The sequence of events for the following case is considered in the diagram. 4 instructions are in the process are at any given time. So this means that 4 distinct hardware units are needed. So here in order to execute this one, so we need to consider 4 distinct hardware units which is considered in diagram B. These units must be capable of performing their task simultaneously and without interfering with one another. Information is passed from one unit to the next unit through the storage buffer. So here we can observe that between fetch instruction and decode instruction there is one storage buffer B1. Between decode and execution, so inter storage buffer B2 is located. Similarly, between execution phase and the write phase, so once again there is one buffer, that is B3. So buffer B1 holds instruction I3 which was fetched in cycle 3. So I can say that buffer B1 holds instruction I3. Suppose if I am considering this instruction which was placed during clock cycle 3 and is being decoded by the instruction decoder unit. Buffer B2 holds both source as well as source operands for instruction I2 and the specification of the operation is to be performed. Similarly, buffer B3 holds the result which is to be produced by the execution of that respective block, and so finally after execution the result can be copied into the write result part. So now we'll consider role of cache memory. Each pipeline stage is expected to complete in one clock cycle. The clock period should be long enough to let the slowest pipeline stage to complete the operation. Faster stages can only wait for the slowest one to complete. Since main memory is very small compared to the execution, if each instruction needs to be fetched from the main memory, pipeline is almost useless. Each stage in a pipeline is executed to complete its operation in one cycle. Hence, the clock period should be sufficiently long to complete the task being performed in any stage. If different units requires different amounts of time, the clock period must allow the longest task to be completed. Suppose if you are having some set of operations and those set of operations can be performed in different clock cycles, or that means some operations it takes longer time to complete the task. If different units, suppose such units if you are combining together and those different units requires different amount of time, the clock period must allow the longest task to be completed. So how I can take the clock period? The clock period is nothing but the time, the longest time, or I can say that longest task which is to be completed. Your unit that completes its task early is idle for the remainder of the clock period. Hence, pipelining is most effective in improving the performance if the task being performed in different stages requires different amount of time. So we can consider a particular instruction fetch phase which is assigned one clock period. So suppose if you are considering one clock period is required in order to execute one instruction, the clock cycle has to be equal to or greater than the time needed to complete the fetch phase. So suppose if you are having some set of instructions I1, I2, I3, I4 and all, but some instruction requires longer time to complete the task, but we have to maintain uniform clock cycle, and while considering the clock cycle, we can consider the task with the longest operation, or the task which requires longest time to complete the operation. However, the access time of the main memory may be as much as 10 times greater than the time needed to perform basic pipeline stage operations inside the processor, such as adding two numbers. Thus, if each instruction fetch requires access to the main memory, pipelining would be a little value. The use of cache memory solves the memory access problem. So that means if you are accessing the information from the memory, so since the size of memory is large, so I can say that main memory is very slow compared to the execution. If each instructions needs to be fetched from the main memory, so at that instant we cannot make use of pipelining concept. But we can make use of cache which is small compared with the main memory, and we can speed up the operation. So when a cache is included on the same chip as the processor, access time to the cache is usually as same as the time needed to perform other basic operations inside the processor. So we can make use of the division of instruction, fetch and processing into steps that are more or less equal in duration. Each of these steps is performed by different pipeline stage, and clock period is chosen to correspond to the longest one. Obviously, so we can overlap the operations, but while designing the clock period, so we can consider the longest task which is to be performed. So we considered the processing of one instruction in one clock cycle, which means that the rate of instruction processing is 4 times that of the sequential operation. So we can speed up the operation by which adapting the pipelining process. The potential increase in performance resulting from pipelining is proportional to the number of pipeline stages. Always the performance is proportional to the number of pipeline stages. However, this increase would be achieved only if pipeline operation is dissected in by considering the different fetch as well as execution phases together. For a variety of reasons, one of the pipeline stage may not be able to complete its task for a given instruction in the allotted time. Suppose if the execution is not completed, the execution of previous instruction is not completed during the next clock cycle. So that is the major problem with respect to the pipelining. The potential increase in performance resulting from the pipelining is proportional to the number of pipeline stages. So we can consider the performance. The performance is basically depending upon the pipeline stages. However, this increase would be achieved only if all pipeline stages require the same time to complete and there is no interruption throughout the program execution. So we are considering one scenario in which we can achieve the better performance only if all the pipeline stages require the same time to complete the task, as well as we are assuming that there is no interruption throughout the program execution. Unfortunately, unfortunately this is not true. Why? Because within the instruction, some instructions takes longer time to complete the task or complete the execution. Some instructions may be completed very quickly, and we cannot assume that there is no interruption throughout the execution of the program. So these factors, it will affect the pipeline performance. These factors will affect the pipeline performance. So in the next video, we'll consider the pipeline performance in detail.